Hi, my name is Wijntjes, and this is my Lab 5 presentation on Faraday's Law. As an introduction, the purpose of this lab was to explore Faraday's Law by observing a magnet falling through a conductive tube of aluminum foil. A time-varying magnetic field can produce an EMF that drives current. The source of the external magnetic field was a falling bar magnet in this lab. The induced current was driven around the tube of aluminum foil. I modeled the interaction between the falling bar magnet and the conductive tube of aluminum foil computationally using GlowScript. The aluminum foil tube slowed the rate the magnet was falling. Experimentally, the bar magnet fell through the tube. It took 1.37 seconds. Computationally, the bar magnet took 1.109 seconds to fall. Some of the physics principles highlighted in this lab were the Biot-Savart law. A bar magnet can produce a magnetic field, and the formula for that is listed below. Faraday's law: a changing magnetic field can induce a current in surrounding objects. A changing magnetic field results in a change in magnetic flux, which then results in an EMF that can be used to determine current using Ohm's law. Below are some of the formulas you can use to do that. Lenz's law was also important. The induced current flows in a direction so that the magnetic field the current produces opposes the direction of the change in flux. Newton's laws were also important in this lab. Some of the methods used in this lab were the use of a magnetometer application to determine which end of the bar magnet was north. I then held the tube of aluminum foil vertically and positioned the magnet just above the top opening. I started recording and dropped the magnet through the tube of aluminum foil and then calculated the time it took the magnet to fall the full length of the tube. These were my data and observations during this lab. The average time it took the bar magnet to fall through the tube of aluminum foil after scrubbing my video and repeating the trial 5 times was 1.37 seconds. This is my computational model I used to create my model in GlowScript. This was the first step. The first step was to get the geometry of the aluminum foil tube correct. I then created a function to calculate the magnetic field of the bar magnet using the Biot-Savart law and the code I used in Lab 3. I then created a function to calculate magnetic flux. After that, I edited this line to calculate the current in one ring, and then I added the next 4 lines to compute a typical B field at each ring. I then calculated the net force on the magnet, and then I updated these 2 lines to find the magnet's velocity and position, and then plotted that, and then printed out the time it took the magnet to fall through the tube. This was the result of my computational model. The time it took the magnet to fall through the tube was approximately 1.109 seconds. Then it was important to interpret the simulation. Red in the simulation indicated clockwise, and blue indicated counterclockwise. If the dynamics of the system were flipped, the same motion would still be observed, but the current would be flipped, because there would be a change in flux direction. Therefore, the color would flip, because the current would need to flip to compensate for that change. How does the total time in the tube of the real-world system compare to the time of the computational model system? The real-world system time was much greater than the computational model total system's time. To make the computational system more accurate, you could account for air resistance, account for resistivity in the conductor, and revisit mu-mag in Lab 3. I used mu-mag in my GlowScript code for this lab. The shape of the velocity versus time plot tells me that the forces acting on the bar magnet after a sufficient amount of time has passed eventually equal each other, and so F net becomes 0. This means that the bar magnet stops accelerating when the forces become equal and there's a terminal velocity. You can kind of see that here. What if the resistivity of the conductor were reduced to close as 0 as possible? How would the dynamics of the falling magnet change? The magnet would have fallen slower, and the magnet would have completely stopped falling if the resistivity was equal to 0. Ohm's law says that V is equal to IR. If the induced current is larger, you would increase the magnetic force acting on the bar magnet due to the current. If the holes or slots were cut into the tube, how would this affect the ring current in your model? The magnet would fall faster, and you would reduce the number of rings, and you would reduce the induced current. This would decrease the magnetic force acting on the falling magnet due to the tube of aluminum foil or the rings in the tube. Thank you.